So for this one, if we're going to evaluate the limit, let's continue just focusing on a function of x and y. So x and y are the two variables here. We can extend this to three variables, but for now, let's understand two variables. So the limit, now we're not just following how x is changing, but we're going to look at it as x comma y is. So as both x and y are changing. So here, let's say we are approaching some values, we can generalize it and say x approaches A, y approaches B. So again, pay attention to the fact that x approaches A, y approaches B. So the limit, as this is what is happening of a function f of x comma y, let's say this is equals to some value L, or this also approaches some value L when this is happening. So either the limit exists or the limit does not exist. Now you have to see one thing here. The logic of what the techniques we're going to use here will literally depend on one thing. If you have a function, doesn't matter what type of function you have. Let's say you have a function like this. And then we're looking for the limit as you approach maybe some value. So someone trying to join us. So we're looking for the value of the function as we approach some value. Now again, what I've drawn here is in the xy plane, but we will use the xy plane to extend the idea to fx comma y. So if the function, let's say, has a given value, let's do it like that. Okay, so let's have this. So let's say we are looking for the limit. So I'll do it for one variable first. The limit as x approaches, let's say 0, for a function that I have here. This is a single variable. In this case, we see that the limit as x approaches 0, the function approaches this point here, the value of y at that point. Now, what you have to see here is that the limit will be the same. Whether you approach this along a straight line, whether you approach that along a horizontal line, whether you approach it along some other weird line, as you approach this point using any particular path, the limit remains the same. So this is the logic that we're going to be using here. The limit of a function x comma y remains L regardless of how we approach this point here, whether we choose to approach it along a quadratic equation, whether we choose to approach it using a straight line. It doesn't matter how we approach the point, the limit remains the same. So you understand what I mean with all these parts when we start doing the examples. But for now, I just wanted to point out that how we approach that point will not really matter. But the closer we get to this point, even if we're using some weird function, as long as when we're getting close to this point, we are coming to this function, not looking at another function that is somewhere on top, but we're looking at a function such that it conforms to this behavior at this point. So basically, we are going to feed whatever this path is in our original function. As we get to this point, the limit will still be the same, regardless of how we approach that point. So we'll look at a few examples to just help you understand what that is. Okay, so if a limit does exist, then as earlier indicated, as x comma y approaches a particular point for a function f of x comma y, if a limit does exist, then we're going to find what that limit is, and that is going to be L. For some functions, it's going to be easy finding what the limit is. But as we go on, we'll encounter some functions which will require tricks for the definition of a limit. You'll see that definition. I think we'll look at it tomorrow. It won't really be the nicest approach, really. Has a lot of words which I don't like in math, but we'll see how it goes. Okay, so in some cases, you might have expressions which are very easy to evaluate the limits for. Just as you saw for single variable functions, some limits just require you to directly substitute and you get your answer. So suppose you have the limit as x comma y approaches, we can go for maybe 3 comma 1. For a function, 3x squared y plus 6x y over maybe 2x squared plus 5y. For simple functions like this one, where substitution does not really result into a problem, you can just go directly and plug in the values of x and the value wherever there's x and the values of y wherever there's y. That is if at that point the function is defined. For some cases, you'll find that maybe at that point the function is not defined, and that is where we will have to start looking at the behavior as we get closer to that point. Here we see that we don't have a problem at the particular point 3 comma 1. So because of that, we will just plug in those coordinates. Wherever there's x, we'll put 3. Where there's y, we'll put 1. For this one, the function is defined at that point. Observe that it's possible for a function not to be defined at a point, but the limit to still exist at that point. So here we'll have 2, 3 squared plus 5, and then we have 1 there. So when we simplify this, we're going to obtain the limit as x comma y approaches 3 comma 1. Here again, we do not have a problem with direct substitution. But this is not always the case. In some cases, we'll not be able to directly substitute. Hence, start looking at some tricks that can work. Before we look at such questions where tricks are needed, any questions on the previous example or not we've done so far? Okay, so let's go with y squared minus x squared over, and then we can go with, let's say, root of y minus root of x. So let's say you have something like this one. Here we see that if we tried to substitute directly, we're going to have 0 minus 0 over 0 minus 0. Clearly, we can see that at the point 0, 0, the function is not defined because we're going to have that 0 in the denominator. So direct substitution will not work for a function like this one. So here, what do we do? Luckily, for this one, we don't even need to start seeing the behavior as we get closer across different roots. Instead, we can just try to rewrite this function or simplify it a little bit. What will happen? What do I mean? Let's just extract the function itself and see how we can rewrite that function. Since we are seeing square roots in the denominator, or should I say, there are two things you should observe here. There are square roots in the denominator, so first you can consider rationalizing that denominator, as in just getting rid of those square roots. Another thing you should observe here is the fact that the numerator is made up of a difference of two squares. So that implies that you can actually split them. So from a difference of two squares, you know that if you have a squared minus b squared, this is the same as a minus b multiplying a plus b. You can try to expand this, you'll see that it will reduce to this. Meaning, since I have y squared minus x squared, I can write this as y minus x multiplying y plus x. The denominator okay, that's someone who's trying to join us. Okay, the denominator, we'll still keep it as root of y minus root of x. Now, we want to get rid of those square roots in the denominator because I do see it's, okay, this one is here now. I do see it's the same structure, y minus x, similar to that. So I should be able to divide so that maybe I can get rid of a 0 in the denominator. So to do that, I need to get rid of a square root so that these two can be the same. So to get rid of the square roots, remember, we can multiply with the conjugate. So since I have root y minus root x, I'll multiply with root y. I'll change the sign on the middle to a plus. Root x. What I do down, I should do on top. The goal of doing this was so that in the denominator, we'll have that difference of two squares that will allow us to remove the square roots without really changing much. So observe that in the denominator, we now have a difference of two squares. By the same concept I mentioned earlier, where if you have a squared plus minus b squared, this will be the same as a minus b multiplying a plus b. It implies that if you have this, we can just look at it as the first term squared minus the second term squared. Implying that, I'm just focusing on the denominator for now, the first term is root y. So it will be root y squared minus the second term squared. The second term is root x. So that is what you get when you expand this. You can try to expand it step by step. You'll see that it will reduce to just this. In the numerator, nothing really changed. I still have x, y minus x, y plus x. But remember, we had multiplied with this. So I'll just include the brackets there, root y plus root x. So that is what we now have. When I evaluate the squares in the denominator, notice that the square roots would disappear. So that now I have y minus x, y plus x, and then here I'll still have root y plus root x, and then in the denominator, now I'll only have y minus x. Notice that now this y minus x and this y minus x gets to cancel, eliminating that 0 which showed up in the denominator, because now my function reduces to y plus x multiplying root y plus root x. So this is now what I have. The function we started with, which is this. We have just seen that it can be rewritten so that it becomes that. So the limit we were evaluating, the limit as x comma y approaches 0, 0 for y squared minus x squared over root of y minus root of x. This limit has reduced to just the limit as x comma y approaches the same point, 0, 0. But now, for a function y plus x root y plus root x. Notice that now we can directly substitute. And if you directly substitute here, the answer you're going to get is going to be 0. So the limit is actually 0. Any questions? Okay. So this one just required this trick. There are more tricks that we can use when trying to evaluate these limits, and they are quite a lot. But in some cases, it might not be possible to just directly simplify, like the way this one simplified. And for those cases, we might want to try approaching our limit using different paths. Since, as we have already discussed, the limit remains the same regardless of how we approach it. Okay, so that is what we're going to look at next. So let's look at a good example for that. So this is going to be our third example. The logic here is, if when we approach the limit using one path, we get one answer. When we approach using a different path, we get the same answer. Then they're speaking the same language. Then we can easily conclude there. So for this case, when we try to use different paths, the thing is, when we approach the limit, let me use what I used earlier. When we approach the point using one route, we find the limit to be that. And when we approach using a different route, we find the same limit. Well, it's pointing towards the fact that maybe that is the limit for our original function. But the only challenge about this is, what if what we have checked is not enough? What if there exists another route where when we approach that point, maybe it will give us a different value? So because of that, this technique of approaching the limit using different routes, mostly we use it only when you're trying to show that a limit does not exist. To show that a limit exists, however, we use a more general approach, because the argument is, even if we check two different paths, they give us the same limit. Check a third path, it gives the same limit. Maybe even path number 4 gives us the same limit. The question still remains, what if there is that one path we haven't considered, which ends up giving us a different limit? So we cannot consider or conclude the existence of a limit by just checking the paths and what they are giving us. So instead, the method for using paths, we mostly use it to show that a limit does not exist. So if we're going to show that a limit does not exist, all we want to find are two paths that we're going to use. And for those paths, if when we use one path, the limit ends up being maybe 3. When you use path number 2, the limit ends up being maybe 4 or negative 3. They indicate different limits when we approach from different angles, hence concluding that the limit there does not exist. The paths usually are chosen. To choose them, just stick to the basics. What do I mean stick to the basics? You pick the simple ones. The simpler, the better. And when the simple ones are not working, then you start picking the slightly more complicated. But depending on how the problem looks like, you can try to analyze the question. You might find a more direct way of approaching it. Here, for example, among the most common ones, you can choose to approach the function along the line x is equals to 0. So meaning you're approaching it along the x-axis. So if you approached along the x-axis, that's the line x is equals to 0. However you approach it, you're setting x to be 0 from the start. Meaning that if you're approaching from along the x-axis, doesn't matter whether you say from the left or from the right, along the x-axis, it implies that the limit is now, remember we had x comma y approaching 0, 0 for the function y squared. Okay, so let me have, instead of this, we have y. So I have y squared plus x squared. Okay, so that's y squared minus x squared over y squared plus x squared. So if I'm approaching along the x-axis, so approaching the limit along the x-axis. So when I write x is equals to 0, I'm basically saying along the y-axis. Yeah, since I said, and I already wrote that, x is equals to 0, meaning I am approaching along the y-axis. So along the y-axis, I'll put that. And the y-axis is the line x is equals to 0. So I am approaching the limit along the y-axis. So that is the line x is equals to 0, implying that where there's x, I'll put 0 already. So now this is 0, 1. Zero, 0, where there is, remember, it's along x is equals to 0, which is along the y-axis. So again, where there's x here, I'll put 0. So this is y squared minus 0 over y squared plus 0. Now, since x is basically not changing, it is 0, our limit reduces to just y approaching 0. No need for us to factor in x. And this is going to be y squared over y squared. And this is basically just going to be 1. So if we approach our limit, our point 0, 0, along the y-axis, our limit reduces to 1. But what if we approach along the y-axis? Along the x-axis, we are from the y-axis. Along the x-axis, what do we find? Along the x-axis, this is the line y is equals to 0. What will be our limit this time? It's the limit for the same function, x comma y approaching 0, for y squared minus x squared over y squared plus x squared. But along this line where y is 0, this reduces to the limit x comma 0 approaching 0, 0. So now where there's y, we're putting 0. And notice that in this case, again, this is the same as just writing the limit as x approaching 0, since y is basically not changing. This will be minus x squared over x squared. Notice that now our answer is negative 1. What does this conclude, or what does this imply? When we approach along the y-axis, the limit is positive 1. When we approach along the x-axis, the limit is negative 1. Because the two limits are not the same, our conclusion is that the limit does not exist. So, therefore, since the limit as x approaches 0 is not equal to the limit, so that's for the function, is not equal to the limit as y now approaches 0. The two are not equal. The limit does not exist. Okay. Any questions there? For this example, we want to see for a function of 3 variables, if the limit exists, we want to show that the limit does not exist as x, y, z approach 0, 0, 0. That is what we want to see. So to show that the limit here does not exist, what do? We can pick any axis. We can choose to approach it along the X, the Y, or the Z axis. Here we chose to go along the X axis. So if we decide to approach this along the X axis, what will be the limit? So first, you need to picture this. If you are moving strictly along the X, so this is 3 dimensions. If this is Z here, and this is Y, and this is X. If you are strictly along the X axis, what is happening? Notice that for any point you pick on the X axis, Y will be 0, Z will be 0. So all the points that you have along the X axis have got Y values and Z values as 0. So if I go for the X axis, then I'm saying Y is 0 and Z is 0. This is what you have to keep in mind. So based on that, when I approach along the X-axis, X is the only thing that is changing as I approach that point, but Y is 0, Z is 0. And then we are approaching 0, 0, 0. So we are presetting the other two to be zeros, except for X. So we have 0 plus 0. And then here we have X squared plus 0 plus 0. So what we observe here is that it's the same as just writing X approaching 0 down here. And then this will reduce to just X. But remember, there was a square here. That square there. So since the other two are zeros, this reduces to X squared over X squared. And this gives us a 1. Now, after approaching along the X-axis, you might be saying, what if I approach along the Y-axis? What are you going to get? Here you should be able to analyze before you even solve, that the Y-axis will not give you concrete information. But let's just try to analyze for learning's sake. Along the Y-axis, as you might guess from the fact that when we are on the X-axis, Y and Z were zeros. If we are strictly on the Y-axis, X and Z will be zeros. Meaning the limit, now I can skip, since X and Z will be zeros, only Y will be changing. And in our expression, since we have X plus Y plus Z, since X and Z are zeros, we'll have 0 plus Y plus 0 for Z as well, squared over, the first one will be 0 plus Y squared plus 0. Observe that this reduces to the limit as this approaches 0 of Y squared over Y squared. Notice that this still reduces to give you 1. So you approached along the X-axis. You got the limit as 1. You approached along the Y-axis. You got the limit as 1. If you approach along the Z-axis, you will still see that here the limit will also be 1. So you picked 3 routes, and each route gave you the limit as 1. Does this imply that the limit exists and that limit is 1? No. This is what I was pointing out earlier. You might pick routes that indicate that the limit exists, yet the limit does not exist. So here, maybe we guessed in such a way that the paths we picked were indicating that the limit exists. But there might be just one route or a few more routes that you might not have considered. And that route might be the one that shows you that the limit does not exist. And here we'll pick a route. Again, remember, these routes can be anything really. We'll pick a route for which X is equal to Y, which is equal to Z. Let's take this to be that for that route, X, Y, and Z have the same value. So if they have the same value, we can even set that value to be in a random letter, maybe even N or A or t. What we're saying is we're approaching along a route where x, y, and z have the same value. Picture such a route to say in the xy plane, it's that route where x is equals to y. That is a straight line slanting upwards like this. So an equivalency in 3 dimensions where x, y, and z are all equal. So notice that now in this case, we're evaluating the limit as x, since they are all the same. Basically, this will just reduce to one variable, and since I've gone that for to be t, we can basically reduce this to where there's x will put t, where there's y will put t, where there's z will put t, and in each case we're approaching 0. So you might as well say as t approaches 0. And then for our function, remember we had x, not x, we had x plus y plus z squared over x squared plus y squared plus z squared. But where there's x, we're putting t. Where there's y, we're also putting t. Z, we're still putting t. And this is squared. Here we have t squared plus t squared plus t squared. The limit as t approaches 0. Notice that in the numerator, we're going to end up with 3t being squared. In the denominator, we're going to have 3t squared. Yeah, I say t equals to 0, sorry, as t approaches 0. So in this case, observe that this reduces to the limit as t approaches, again I went for equal, t approaches 0 of 9t squared over 3t squared. The t squared cancels, and this reduces to 9 over 3. 9 over 3 will be equals to 3. So in this case, we see that the limit has reduced to a different value. So the fact that we have found that there are routes which have different limits as we approach the same point indicates that the limit does not exist. So that becomes our conclusion. Any question? So there are more examples we can look at just to show that the limit does not exist. I think tomorrow night we're going to do a few more examples to just help you guys get a good understanding. We're going to look at examples where maybe you have to approach along a quadratic expression and where you have to approach maybe along y is equals to x and so on. They are really, really quite a lot. So we'll see all that